continues to work as I proceed.
All right, excellent.
Alrighty, so I'm talking about astrometry today, and I'm going to split that into two pieces. And I think the biggest piece, and actually the hardest piece for most people who work on astrometry, which does not include me, by the way, is astrometric calibration. And this comes down to how do we model the effect of the observational system on the position of objects, and how do we constrain that model. After that, in the second half, I'll talk about astrometric measurements, which is essentially how we model changes in the positions of objects. What are the actual the motions look like from an astrophysical sense, or something a little bit closer to an astrophysical sense, and how we constrain those models. And obviously, constraining those models will have to take into account somehow those astrometric calibration models that we had before. So I'm going to go off by saying what we mean by WCS and PSF at sort of a low level, so we're all on the same page. So get a true astrophysical scene, some true set of galaxies and stars, in which stars are points, delta functions in sky coordinates mu, at wavelength lambda, the value of a pixel in some image j at position x, and time for the whole image is given by this integral. We have some transfer function t that we integrate over with the true scene, and we integrate over both position and pixel coordinates, and the position of the true object and the wavelength. And one of the fundamental assumptions of doing sort of this kind of astronomy is that in the neighborhood of any given object, we make this approximation. We say that transfer function is some photometric calibration term, this tau, which we're basically going to ignore from here on out, that this is constant over this object, that you have this point spread function. In other words, that this thing acts like a convolution on the true scene. Oops, I realized I left in the true scene term over here, even though it's not part of T. Sorry about that. And then this A term, which is what I'm calling the world coordinate system, the WCS. And that's just a transform from the sky coordinates to the pixel coordinates. And in this case, I'm defining it so that the transform is from pixel coordinates to sky coordinates. So obviously, if we go from sky coordinates down to pixel coordinates, that's the inverse of that transform. So what I've said a little bit here is that PSFs and WCSs have these properties. Well, the first one is that things are locally constant, or in the case of the WCS, locally affine. And this is a really fundamental assumption. It's necessary for treating the action of the PSF as a convolution. If you don't have these two things, you can't treat the PSF as locally constant and the WCS as locally affine. You cannot treat the PSF as a convolution. And in fact, you cannot split up your WCS and PSF. It's some more complicated integral that you have to do in a much more careful way. We're also defining the PSF to be wavelength dependent and the WCS to not be wavelength dependent. And this is a convention at some level. I'm pretty certain that there are wavelength dependent terms that have to be considered part of the PSF because they act like a convolution and not like a coordinate transformation. I don't think under this first approximation, this locally constant approximation, that there are any terms that you can't treat as a convolution. In other words, you can treat a shift due to, say, DCR as a convolution in this approximation that things are locally constant and locally affine. And so that's what we're doing. Because we don't have to make both of them wavelength dependent, we're only the PSF wavelength dependent. We're also, of course, assuming that things are not time varying with exposure. And that's a simplification that shouldn't do any harm because we're not concerned about things that are changing or moving that quickly. And at some level, if we were, there's not much we could do because we can't constrain the PSF and the WCS on time scales shorter than the exposure. But before I go on, I should mention that these all-important assumptions that we're starting with are violated slightly by various sensor effects. And I'm not going to spend a lot of time going on about sensor effects, but I wanted to make you aware, at least that the level I am, because I don't follow this too closely, what effects there are and what they do. And so by and large, these are sort of problems in the images that we have to fix before we can make that fundamental assumption. And that includes things like brighter, fatter, which make it so the PSF is not an evolution, or at least that's one way to think about it. There are various ways to create lateral electric field sensors that shift essentially the boundaries of pixels around. And enlarged, we can handle those three different ways depending on how strong and how smooth they are. So if they're smooth, then we don't care that these are coming from the sensors rather than coming from some other physical part. We're going to fold them into the WCS because they don't violate that assumption that the WCS is locally linear. If they're sharp but weak, then we can probably interpolate neighboring pixels, not in a super principled way, but because it's already a very small effect, we can do something that's a sort of a first order correction and not worry about higher order problems in that correction. If things are both sharp and strong, then we don't have much choice but to mask out the pixels. Now, and we probably will have to mask out some pixels around the edges of chips, but we don't, and perhaps in the middle where we have some edge-like effects between amplifiers, but we don't expect to have to mask too many pixels for this. There are sorts of a charge transfer inefficiency-like problem. There's plenty of literature on charge transfer efficiency, although it would be different if it's for our case than it is for, say, the CTE problems in Hubble. But I'm not going to, that's definitely out of scope for this talk. And then there's, of course, the regular QE nonlinearity. You can derive a correction for this from flat fields, and then you can just fix it in the images with some sort of table or polynomial lookup. It's worth noting that most of these introduce correlations in pixels. You can sort of fix them at the right level, but they are going to correlate pixels. It's not clear to me whether any of these correlate the pixels enough that we need to propagate it. If we do, that's unpleasant and potentially expensive, but it's also very straightforward. So if we can make all those assumptions, this is how we would like to model the PSF. And I'm going to use two, we'd like to split it into I'm calling it 4 different terms. You can count them slightly differently if you'd like. Let's start with the term for the pixels. Do you have a question there? All right, sounds like no.
Yes.
Oh, go ahead.
Yeah. Do you expect some effect from, for example, it is expected some extra light when you point the telescope toward bright sources or something like that?
Yes, so that kind of ghosting.
For example.
Yeah. Well, if I understand, I think you're mostly talking about ghosts, and those do behave like a PSF. They are convolutional. They're a hard part of the PSF to constrain, but I think the first order at least will be able to include them in the PSF.
I think on this particular optical design, there aren't any nearby ghosts.
All right. Any other questions on sensor effects before I move on? Alrighty. All right. So the PSF. I'll start with what I'm calling the pixel term. This is just the pixel response function. So you have some diffusion in the pixels, or other things that, and of course the actual integration over square pixels rather than just sampling goes into this part of the PSF. This is something we would fit in what we call calibration products production. This is the same part of the pipelines in which we build master flats and biases. We would also build a pixel response function for the PSFs. And then when we actually fit in data production, when we're trying to fit the PSF of any particular science frame, we would hold this fixed. The next part is a relatively big part. This is the optical PSF. And this is something where we would figure out what a set of limited degrees of freedom are in the calibration products production, and then we would fit those limited degrees of freedom only in the data release processing, the actual pipelines. This would hopefully include all the discontinuities between sensors, because those are basically just focus differences between sensors. And we'd like to do this with Zernike polynomials in the wavefront domain, and that's the way the code that we're working on works. This is mostly work by Josh Myers. The next term is the biggest. This is the atmospheric PSF. There really isn't much you can learn about this, so we have to fit it separately in every science frame. We'd like to do one per bit model. So because the discontinuities between sensors are handled in the optical part, this should not have to have any continuities between sensors. I don't think that's really ever been demonstrated certainly not at the level that we need to do it. but it should be possible. And for this, we're thinking something like a pixel basis model that's interpolated either with polynomials or Gaussian processes. The last part, I think you could have considered part of the atmosphere, but it's worth calling out as being different because it has no free parameters and it has a very predictable wavelength dependence. And this is the DCR term, the differential chromatic refraction. This is something we can add into the PSF much as we would add in the pixel or the fixed part of the optics. And that gives us automatically one of our most important chromatic PSF effects. It's not our only chromatic PSF effect. The optics and the atmosphere both have their own wavelength dependence that we can mostly know physically, although I think it's a little bit different for the atmosphere because we can't really we definitely can't assume just chromograph seeing. But at least we can, for all these components, come up with something like the chromatic dependence from physics. However, I think it's probably unlikely we'll be able to do exactly that. And I think the real we use is going to look a little bit more like this, where we would like to have those four terms, but the actual model we have has basically one component for the constant instrumental contributions, the pixel part, and the degrees of freedom in the optics that we can characterize well. And then I think there's going to be some degrees of freedom in the optics that we can't characterize well, and we basically roll those into the atmosphere part as well because they're basically degenerate. And the DCR part, I think, continues on not having any free parameters. So this means that the wavelength dependence of that first blue part, the constant and well-characterized distribution parts from the optics, we do know what that is from physics. The wavelength dependence of this brown part, we don't know from physics. We'll have to learn that empirically from the colors of the stars that we're putting into the models. So how do we actually do the PSF? And I think it's just, with some scare quotes, forward modeling the images of stars. This big fancy model, and we want to make that model reproduce the images of stars. In the calibration products production, the parts of the PSF we want to constrain there, we would use in-focus and sets of out-of-focus exposures, probably of dense star fields, and possibly the wavefront sensor images from these exposures. You can learn quite a bit from how the optical PSF is behaving in particular from looking at those in and out-of-focus images. In the actual data release production, when we're fitting the science frames, all we have are the stars in the in-focus science exposure and possibly the wavefront sensor images. I think there's some very preliminary work that suggests on DECAM data that suggests that maybe those wavefront sensor images aren't as useful as you would naively think. But certainly, if you're thinking naively, the wavefront sensor images seem like they've got to be very useful because they are in and out of focus images. It all depends on how much the information at the edges of the field are relevant for constraining what the PSF is doing in the middle of the field.
Jim, Tom Laredo has a question. Tom, do you want to ask it yourself?
It was just back on the previous slide or two slides ago. I was just wondering, what is the metadata that gets used to figure out the DCR corrections?
It's basically the pointing of the telescope and the air mass.
So, okay. I didn't know if it was measurements from the auxiliary telescope or what kind of stuff.
I don't think so. It does depend on the air pressure, but I think pretty weakly, and I'm not sure if would even be necessary for us to fold that in. Robert may have an opinion.
Okay.
I don't know whether the humidity matters enough to worry about.
Alrighty. Okay, moving on to the WCS. So just like the PSF, we would model the WCS as a bunch of different components. Here, instead of convolving those components, we're composing them. So these are each coordinate system transformations that are composed together, and you can think of each of them as representing a different coordinate system. Although in some cases, maybe it's the same coordinate system. Well, no, I guess they're by definition different coordinate systems. So let's start over here on the left. And this is just smooth sensor distortions. These are those things I talked about in the previous table that may come from the sensors, but they're smooth enough that we can consider them part of the WCS. These are baked into the sensors and fixed, so we can fit those in the calibration products production and hold them fixed when we're fitting science frames. Next up is just a rotation, translation, scaling of the sensors with respect to the focal plane. They're not quite in the regular grid that we hope to put them in. This is something we can certainly fit pretty well in the calibration products production. I think we probably ought to be able to fix it in DRP. There's some chance that things might wiggle when we move the telescope, but they certainly won't too much. And if we do have to fit anything for every science frame based on what the telescope is doing, hopefully we reduce the degrees of freedom that we're fitting there as well. That essentially applies to this optical part as well. The optical distortions are the biggest part of the WCS, and I think they're very close to fixed, and we can determine that in calibration products production, but we'll probably need to have some perturbation allowed per visit. And that perturbation might be entirely degenerate with this next term, the atmosphere, just in the same sense that the optics was somewhat degenerate with the atmosphere and the PSF. There's also atmospheric distortions due to the PSF, and we have to fit those per visit. We can't really learn much about them, except maybe their power spectrum in calibration products production. And the last piece is just the very simple tangent plane projection that we're all used to from FITS WCS. And this is also, you have to fit it per visit, but it's just a couple of. So how do we constrain the WCS? And this basically again involves just forward modeling, but we're forward modeling the positions of stars and possibly galaxies. Galaxies are not useless at these depths, even if you can't accentuate them individually quite as well. There's just a lot more of them. We're forward modeling those positions, through this big composition of coordinate transforms on multiple overlapping. So we have information about, we know the same object is on multiple different images, and it appears in a different place on all those images, but it has the same place, the same position in the true sky or something very close to it, and we can model those differences by including proper motion in the model of the objects. And of course, we'll also include Gaia positions, reference catalog positions, which is for LSST, once we're in operations, is certainly going to be Gaia, and that will be much more powerful than tying to reference catalogs has been in the past, because the Gaia catalog is much better constrained, and it really is a rigid system that we can tie to. So to a large extent, we're essentially just mapping out the coordinate transforms on spatial scales that are smaller than the distance between Gaia stars. Because we're going deeper than Gaia, we will have stars between Gaia stars, and we will have to constrain the coordinate transforms on those scales, because the atmosphere is doing things on those scales. But we really do expect to trust the Gaia's positions to really nail things down above that. So for all the terms that we want to fit in calibration products production, we could use dense star fields again. It probably would work to just use our deep drilling fields. I think you gain information about some from having more stars or more objects per exposure. You gain information about other parts from just having many exposures. My intuition is that just having many exposures is what wins in this case.
Jim, so what is the angular scale for Gaia? Like what's the scale at which you were basically having to do LSST specific constraints here?
Oh gosh, I don't know, but let's see the number of. I don't have a good intuition for what the Gaia density will be in their final catalogs. I certainly know that their catalogs right now are very sparse, and there's quite a bit to fill in. I would guess that somebody else on the call knows this better than I do.
The density varies greatly with galactic latitude,
sure.
But roughly speaking, to LSST depth, we expect to have about 1 star per arc minute on average, useful for calibration, and to Gaia depth, it's 1 star every 5 arc minutes or so. So we would have a handful per CCD.
I think it's about 50, something like that. 50 at latitude is the number I remember. Yeah. 50 per CCD.
Thanks,
at high latitude.
Yeah, which is pretty good. That lets you constrain a whole lot of this model. If the model wasn't quite so sophisticated, if we weren't pushing so hard on the systematics, that would probably be sufficient. All right, so then that's what we do in calibration products production. In the data release productions, we're fitting in units that we call tracks. I have been envisioning this as a region about twice the width and height of a focal plane, just because you want to get multiple full visits in each fit. But above that scale, we would totally rely on Gaia to tie things together. I think it's still an open question whether we would try to fit multiple bands together for the astrometry. We certainly need to match multiple bands together, just because a lot, as you've seen, we have a lot of chromatic dependence in the PSFs, and we need to be able to know what the SEDs of objects are on smaller than the PSF, and we're going to infer that from the broadband colors. Before we get into that, I should talk a little bit about how we bootstrap this model and what we do in alert production, because so far I've talked about data release productions and I haven't talked about alert production. And basically the difference here, both in bootstrapping the data release production results and the calibration products results and the alert productions, is that we're processing one exposure at a time. So for the PSF, that means we fit an empirical model. It's a pixel basis, probably polynomial interpolation. That's sort of the state of the art right now, and it's not clear that we need to do better than that for this purpose. I think we can get away with fitting every CCD independently with no wavelength dependence. And of course, when you only have one exposure at a time, you don't have any information about what the SEDs of those are, so you don't really gain much from adding wavelength dependence to your PSF. For the WCS, you're basically an empirical mapping from the positions in the exposure to reference catalog positions. But this is not necessarily worse than the full model if we're using joint cal, that procedure I talked about before, to make a sufficiently dense reference catalog first. So we do think that astrometry is very important for difference imaging and for alert production and for reducing false positives there. But we're not running this full joint cal procedure because basically we can do that up front. At the same time we produce the temporal difference against, we'll also produce a very dense reference catalog. It'll be a combination of Gaia stars and LSST positions that have been calibrated to them that we can then use to calibrate any additional exposures we get. And I believe the requirements for doing observations of an area of sky before you can run the alert productions on it is the same for generating this deep reference catalog and for generating a template. If you can make a template, then you have enough information to make this deep reference catalog. So where does this all fit in? So this is a snapshot of a flowchart of one piece of the data release pipeline, sort of the first piece where we start from raw images. And basically we'll construct these initial PSFs and WCSs essentially the same kind that we would in alert production in this bootstrap stage. We'll go improve the WCS based on those measurements in joint cal. That will give us improved WCSs and improved photometric calibrations and improved source positions. And then using those improved source positions, we can go and then improve the PSF and come up with this more physically motivated wavelength dependent PSF. Now, I think after that, this is the first time that we'll have access to wavelength corrected positions. So we'll probably need to feed that back into another round of joint cal before we're done. And it's possible we'll need to do the PSF modeling again after that, but I suspect just one iteration there is all we'll need to converge. All right, so that's it for calibration. It's a good time to stop for questions before we move on to measurements. All right, sounds like I've given you all enough time to unmute quickly and say something if you wanted to. If not, please shout, but I'm going to move on. All right, so I mentioned this a little bit before, but using wavelength-dependent PSFs requires actually knowing the subband SED of the object being measured. This is not something we observe directly. Our plan for this is to infer those SEDs, the subband SEDs, from the broadband colors of objects, essentially saying that the G minus I color tells us roughly what the object is doing inside the R band, for instance. We are not currently planning to use the PSF information, such as DCR, to constrain those subband SEDs, except in one little exception that I'll get to later. So it's worth pointing out, this means that we might infer the SED of the object you care about and thus make incorrect measurements on it because we'll be using the wrong PSF. We do plan to make it relatively easy to go back and use your own preferred SED, but because PSFs are really fundamental for any kind of image processing operations, trying to evaluate the PSF with your own SED instead of the one we picked will in general require doing some image processing. We might take some derivatives and expand things out in terms of how things change with respect to SED changes in some cases, but I think in general plan on that requiring some image processing. So first kind of astrometric data product I'm going to talk about are source positions. So this is the source catalog. These are single epoch detections centroided on just that epoch, the simplest possible thing. This uses our best PSF models and WCSs. We're going to update these after we have the improved ones. but because we don't actually have any subband SED emission, because we don't have the broadband colors for the sources, we're probably going to get something like DCR and the other chromatic parts that be wrong in a predictable and somewhat easily correctable way. As I said, you might still have to do some image processing, or you'll have to have a first order approximation for what DCR does to the position of an object, which in the case of DCR should be quite accurate actually. So if you don't like the assumptions we've made in the models I'll talk about in the next few slides, you can go back to these source positions, you can match them, you can correct the positions based on what you think we did wrong with the PSF and the SEDs, and you can fit some motion model to these positions if you don't like our assumptions. Next up is the astrometric measurement that I think most people will want to use most of the time, at least if you're concerned about moving stars. And these are the moving point source fits in the object. So these are multi-epoch PSF convolve fitting in which we have free parameters for the position, the proper, and the parallax. And so this is really a forward modeling of everything you really care about in looking at stellar motions. The PSFs in this case will be evaluating using that subband SED we inferred from the broadband colors. I think that'll be just fine for the vast majority of stars. And when that's the case, this should be our best stellar motion parameters. There's been some demonstration of this kind of effort before, Langenhag 2009, and the real advantage of that, of using this approach rather than just fitting the sources, is that it gives you a better signal to noise, even to the point where this should work on objects below the single epoch detection threshold. Even if we have to, look at the coas to detect these objects, we should be able to say something about their motion, given all the input images we have. It may not be very well constrained, but we'll be able to say something.
This is Tom again, sorry. So will every object have all of these parameters, or is there going to be some criterion where you'll just say, that's too far, there's no parallax, so we'll turn off that parameter? And then also...
Our current plan is to...
Go ahead.
Oh, go ahead.
No,
our current plan is to fit these models to everything. Even if we're relatively confident that the object is a galaxy, we will fit these models. And that's partly because these models are one of the components that we'll use to try to determine whether the object was in fact a star or a galaxy later.
And is there some prescription already in place for how to summarize uncertainties, like even in the low signal to noise regime? Like things like parallax are one-sided, so you need to think of how to do that. So
that's a good point. I think the uncertainties that we have sort of spec'd out right now are just Gaussian. We've talked about having Monte Carlo drawn from likelihoods for other parts of the model. It's something we could consider doing for these two, as long as we don't need too many samples.
Okay, thanks.
All right, the next up is the DIA object catalog also has moving point source fits. So these are catalog space fits to the set of DIA source dipole measurements associated with the DIA source. So what happens is we detect a DIA source in a difference image. It looks like a dipole, and we can measure the properties of that dipole, which gives us some indication of both the flux and the separation, but in a highly degenerate way. And of course, even if something isn't a dipole, you can fit a dipole to it. It's just sort of it's a dipole with no sub. And so what we can do then is take all of the source measurements that are associated into a single DIA object, and we can do a fit to measure proper motion from those measurements. This is only measured for things that are detectable in single epoch difference images, so it doesn't go as deep as object. And at least early in the survey, where we don't have a long baseline, we're not going to even have DIA sources. We're not going to see any difference for objects that are moving slowly, because they just won't appear in the difference images. That said, these may be our best measurements in crowded stellar fields, because using the difference images removes a lot of the crowding. If you have stars that aren't moving very much and you have some that are moving a lot relative to them, you will definitely see those dipoles in the difference images, whereas it might be impossible to see them in the direct images.
But Jim, you need to know the direct flux to interpret those dipoles in terms of emissions.
Yep, I was thinking about when putting these together, these slides, and I'm not sure if that means that we end up with a motion model that has very weird degeneracies in it, or just very large uncertainties. I think this is an area where we have not thought enough about how we would actually constrain these in detail. All right, so I mentioned image differencing, but I haven't talked yet about how we actually handle these chromatic PSF issues in image differencing. And I think it's clear that to cleanly subtract images, you have to account for the wavelength dependence of the PSFs when you construct the difference image kernel between images. And so the plan we have for this is roughly given by this equation here. So we have the actual image Z, and we're going to subtract some coed image C. But we can involve it with the difference kernel first, and that's split up into a few terms. So first, we have this normal difference kernel. This includes all the other PSF differences. This is the normal thing you would do if you were not worried about chromatic PSFs, and it's just constrained from trying to match the coad to the science image you're trying to difference it with. But instead, we're going to have this sum over wavelength bins. So instead of having one coad, we'll have subband coads for different wavelength bins within a filter, within one bandpass. And for each of those, you can construct essentially a DCR difference kernel that maps the DCR that you effectively got on the coad to the DCR that you see on the image, and for that wavelength bin. And so this really involves some kind of deconvolution. And certainly all these different coads, subband coads, are going to be highly correlated because they're derived from the same image, from images that don't have any subband information aside from what's available from the chromatic PSF. But when you add them all together, that should get rid of a lot. That should put those correlations back together into one image, and we should be able to do this subtraction. It's worth pointing out that this is primarily for DCR. And that means we're going to focus this work on the bands where we have DCR. So we will almost certainly have multiple wavelength bands inside the G band. We might have it for U and R band as well. We probably won't for IZY, where the DCR is really negligible. But it's worth pointing out, those of you who are interested in what the wavelength-dependent PSF tells us about the subband SEDs, all that information is in these subband template coads and the between them, which we also have to record. And of course, these are coads that we're going to have to, retain after the processing and data release is done, because we're going to use them for alert production for the next season. So these coads will be available, and you would have to do some image processing on them to learn stuff from them. But I think all the information wavelength-dependent PSFs tell us is in those coads. I also talked about measuring faint stars that might be too faint to appear in single epic images. It's worth pointing out that some stars are both too faint to appear in the difference images, but they also move too fast to add coherently in the multi-year coed. And it's some of these are moving so fast that we don't have any way to detect them. The information isn't there. But for other ones, we'd like to try to create some short period coeds. I think the nominal cadence is probably yearly. Difference them with the deep coeds, and detections in that difference image and in that difference would also be included in the object catalog. Now, anything we detect that way should be fit just by that these object moving point source fits, because those go back to the original images. They include the information we have available, and the trouble is just detecting them. And detecting them is what these short period coeds are for. But these coeds will not be retained after processing is complete. Like everything else we produce, it should be possible to regenerate them, but that could have rather high latency that might, cost a bit in terms of processing time. Finally, I should say that the DRP team has been investigating some improved coad techniques that we think might make the multi-epic fitting unnecessary for galaxies. Now, that's, you might think that has nothing to do with astrometry, but if we get rid of multi-fit for galaxies, it would be highly desirable to be able to get rid of it for point sources as well, and that leaves us without a way to do what I just said was our best measurements of object proper motion dynamics. So we've thought about this a little bit, but we haven't really investigated this seriously. I'm not sure it's even fair to say we've thought about it very seriously. But I wanted to throw the rough ideas we've got right now out to you guys. See if you have any more clever ideas, or if you have any ways in which this idea would, is obviously unacceptable in a way that wasn't obvious to us. So the basic idea is that you fit the same, forward model PSF convolved to the short period coads instead of to all of the input epochs. And that doesn't give you as much of constraint, because on any one of those short period coads, things are smeared out slightly by the motion. But I think you can get quite a bit from that, because at least for most things, most stars, things aren't moving very far in those short period coads. When you do the force photometry, then we use the positions from that model, and we compute force centroids as well, which is essentially saying, given this filter that I put down, that from what my model says the object should be, compute the actual centroid, which is some small delta from what that model originally says. And then you can model with the force centroid. And the premise is that the short period coads will get us close enough to where any updates to the model sort of are in the linear take 1 Newton step kind of regime. And the force centroids will be enough to get us the rest of the way there. I'm particularly worried about whether this works in the case of objects with very high parallaxes, of which there will not be too many, but we certainly don't want to miss out on them. And that's actually all I had. This ended up being a pretty fast presentation, so hopefully there'll be some interesting discussion afterwards. My summary slide is a bit of a table to tell you, what data products you should use when. So I'm not going to go through every possibility here, but I think that the fundamental questions are: is the object moving? Do you SED? Is the object in a crowded field? And are you trying to infer the object's SED from the chromatic PSF? And for various combinations of answers, I think we've got some data products that will do what you want, and I think this answers most of the most common cases. And of course, if you can't find a cell that matches or a row that matches what you want to do, you can always do custom processing in the science platform. And I think that's about it. Any questions?
Oh, Jim, you were too clear on this presentation. There are absolutely no questions. So one thing that comes to my mind is that this may be a good place to begin planning a cross-collaboration, crowded field little phone call to understand what the various collaborations are thinking about crowded field photometry and what collaborations are interested in specifically developing data products for crowded field photometry. I know a couple of collaborations are certainly thinking about it. And I had threatened you all before with adding another phone call to our list of communication to foster intra-collaboration, work between collaborations. So expect me to contact you all and try to set this up. I think after this presentation, it may be a good time to start thinking about it more seriously. Any further comments or thoughts or complaints?
Well, I'm surprised we're not hearing more complaints, which worries me that people are so horrified that they can't possibly imagine saying anything. We've
Don't worry,
received
Robert.
a
I'm
lot.
working on it.
Okay, great. I'm glad Dave's there. I was about to say, if Dave Monet were on,
he is on. He
is. Fortunately, it's good. It was so good to have Dave on. He normally complains that this isn't the way that real astrometers do anything, which I don't think is actually quite true. And I think it's partly because Dave sees the letters WCS and thinks evil Calabretto and Grice and horrible papers that we all hate. I hope that Calabretto and Grice.
I see the letters Princeton and think horrible thoughts.
Yeah, that's right. It's all Gun Sensei's fault, Dave.
Mike,
seriously.
Since I don't understand any of this, my first real question is, does this work? Has anybody ever tried this algorithm on data and compared it with traditional astrometry done by clueless fools such as myself? And if not, is there a chance to do this before we commit to this algorithm and sign off in blood and saying that, yay, verily, this works, and we, the LSST science collaboration, believe this? And I'm more than casually concerned, but it's not obvious how to proceed. I mean, in a month, we will have Gaia DR2, which will, for all intents and purposes, be the reference catalog for LSST. And we also have infinite amounts of data from dark energy camera or hyper prime camera or other things. And so the question would be is there a reasonable data set that we could convince the Princetonians to give us the right answer on, and let the Union of Concerned Astrometrists play with it with obsolete algorithms, and keep some positions out and keep some objects out and motions or parallaxes, and then sort of at the end of it say, did we both agree? And if so, then we will applaud wildly and let you and condone the Princeton activities. I am more than reluctant to sign off on such a complicated algorithm with so many relatively free parameters, when that just flies in the face of decades of astrometric experience. Sorry to go on.
So you're talking primarily about the model for the calibration model, the model for the coordinate system transformations, right?
Well, I'm worried about everything, of course. But for example, one of my pet projects, which I actually can get paid for, is to get absolute positions of radio QSOs with the VLBA, and they come out with RAs and decks that they claim are accurate to tiny fractions of a milliarc second. I then go to the LSST catalog and saying, okay, let's look at the RA and deck that LSST just published, and some ensemble of these objects will tell us if there's any mean rotation between the radio and optical coordinate frames, which is an active area of concern for a large number of people. And so when I see iterative algorithms that start with a robust estimate based on Gaia, but then can wander off in the way that all iterations wander off, I really worry at the sub-milliarc second level as to whether I can simply subtract my RA and deck from your RA and deck. Is LSST on the Gaia system to mean 0 and sigma, whatever it is? That's a huge concern. That astrometry is not two-dimensional photometry. You're not allowed to come up with your own internal coordinate system that's kind of like this, except it's not quite. It's not fair to ask a user to transform to the LSST system of RA and deck.
Yeah, so I think on large scale, we will absolutely be on the Gaia system. I think if the complexity of our model does any damage to tying ourselves to the Gaia system on large scales, that is a bug, and we will fix it.
Well, how do we test for
on
it?
scales below Gaia? I don't know whether it's better. I think there's a risk of overfitting, and you have to not overfit.
And again, the question
I also think you can't assume things are just smooth. Sorry, go ahead.
I'm sorry. The question is, can we do risk reduction by trying this algorithm prior to signing off and saying this is the production algorithm for LSST?
Yeah, we are working on that. I think that the progress on that has not been as fast as we'd like, but it is progressing. The models are sort of upping in complexity. I think I would not want to draw too much from that before we have a Gaia catalog of something approaching the density of what we'll have in the end. But yeah, I do expect that we'll be able to do that.
April 25th. DCR2.
So Dave,
2 is coming out of the.
So GDR2 is April the 25th, and we're already using the GDR1 catalogs.
Right.
We are reducing HSC. Yeah.
No,
So.
Yeah, hold on, Dave. Let's hear what is actually being done on the Gaia catalog, please.
So we're using the Gaia catalogs. We will switch to GDR2 shortly after the April the 25th. I don't guarantee it will be the 26th rather than May Day or something like that, which will be appropriate for the GDR. We will be using probably HSC data on that. HSC has the advantage of an ADC. There's DECAM data you can also test relative to that. as Jim said, we're worried about overfitting. The normal way to detect overfitting is to hold back some candidate stars. So we will hold back some subset of the Gaia star to confirm that they are indeed moving at zero velocity relative to the LSST frame. But there isn't an LSST frame. As Jim says, it has to be on the Gaia system. You can go and try to see whether quasars are moving relative to that. I worry about color terms in quasars. But yes, we will do all due diligence. The numbers coming out from some very preliminary versions are that the scatter we're getting is something like 7 milliarc seconds, I think, in the multi-epoch fields. That's not a tenth of a milliarc second, but it's better than the US Navy did on Sloan by a factor of 10, which is a totally unfair comparison, I might point out. So you're quite right to be suspicious, but I don't think you're right to think that we're not going to try to make you happy, and that the approaches being used are indeed not all that different from the way you've always traditionally done it. You've described it a little bit differently.
Well, I did not mean to be disruptive in saying that you...
Wait, Victoria, can you please call?
Yeah, so
Okay.
I think that not being disruptive, Dave, asking questions like how are you going to confirm and when how good astrometry is relative to Gaia is a totally legitimate question. And say, I want to run these tests because I don't trust people in...
Let me suggest that we open a specific issues on community where we can keep each other, up to date about how your testing is going, what are your next steps that you're planning on in these tests, and what the results are as you guys produce them, so that we can ping you there if we don't feel like your tests are coming through timely. So of course, politely ping you, and then we can get updates on how the tests are going. Does that sound like a reasonable plan? Dave, do you think that will help you feeling a bit more comfortable about this?
Works for me, sure.
Excellent. So I will definitely open a community post and specifically invite you, Dave, Jim, and Robert, and of course everybody else as well. There's another question by Megan. Megan, do you want to ask it yourself?
Sure. Sorry, I'm in a hotel room in Cumbria, Portugal for a KBO conference, but hopefully the internet's good enough. Just curious about the difference between source and DA objects for if this object is moving. Just looking at the final table, it's just a little surprised that only source is available as like the third option for if its object is moving, but I don't care about the SED and it's not in a crowded field. I guess because I figured that all moving objects were from DAO object, that source and DA object would be exactly the same. So is there a difference between them when it's crowded versus not? I guess I always assumed for moving objects it would be exactly the same because they're found through the DA object. So I was just wondering if you could go a little bit into detail why on that third line they're equivalent but not above.
Yeah, I suppose that the information in those is not very different. But when you do difference imaging, you introduce a little bit of noise, and I think, and of course you have this problem of you need to use that Robert brought up that you can't just use dipoles. You need to have some measure of the absolute flux as well, and so using the sources I think is sort of a simpler and ever so slightly less noisy way that has essentially all the same information, as long as you're not being hit by crowding. If you're being hit by crowding, the advantages and simplicity of using just the sources goes away. But there isn't a big advantage of using this over the DA objects, again, assuming we can solve this issue that Robert raised of how do we get the absolute flux of objects to sort of break that degeneracy in the dipoles.
Mm-hmm. So then will the sources be available, or is that like more in the annual release, but the DA objects will be available on that nightly timescale, or are both of those going to be done at the same time for moving objects? Do you know?
I do not believe that we are putting out sources in the alert production, and the DIA objects in alert production are not going to have a tremendously long time window. So you're not going to get anything but relatively fast moving stars there because the baseline just isn't there. or at least you'll be missing a lot of information relative to what you can get from the data releases. I think for the most part, you're going to want to use the data releases for any sort of astrometry, unless you have some to follow up quickly based on what you get from the alert productions.
All right, thank you.
Right. Any other questions or complaints?
I guess I wanted to ask about the SCDs, if that's okay. This is John Gizes.
You have my blessing.
Yeah. So, I mean, is this? I don't know how sensitive are these sorts of things. I mean, do you care about a galaxy SCD versus a stellar SCD? One red source versus another. I mean, what's the level that this matters at? I don't have a good feeling for it.
So the biggest effect, I believe, by a fair margin, is DCR in the G-band. And that's going to be a big difference for, very red versus very blue objects. I don't think you need to deal, I think if you split the G-band in two, you wouldn't really have much in the way of problems anymore. And I think that's at least how I think about how serious these things are in terms of, what we can get away with in terms of approximation. So that means we can probably, split the G-band into just two wavelength bands and then be fine in terms of at least, difference limit subtractions and probably, photometry. I have not thought really or tried to look at the numbers for how those offsets would affect astrometry. I suspect that comes down to how the, distribution of air masses interacts with the number of observations and where you were pointing when you looked at various stars.
Yeah. One of the cases, John, is people worrying about looking for quasars, while Lyman alpha swings through the G-band. And then you can potentially get quite a significant astrometric shift, which is of interest, which is one reason for allowing general SCDs instead of just correlating it out by color.
Okay. Anything else? Well, we are 6 minutes to the end of the hour, so I think if there are no other questions, we can stop here. I don't have the data at the top of my head for the next meeting, but it's somewhere towards the end of next month. You will be notified about that as usual through your calendar, your PST calendar, Slack, email, pigeons, all the usual means of communication that I use to communicate with the SC chairs and the project. And thank you very much for attending, and please let's continue the discussion on community. It would be very good if we could continue debating these issues there and keep the discussion alive. Thank you very much. Thanks, Jim, for taking on this, even though you're not really an astrometry person.
Thanks, Jim. That was really interesting.
It was really interesting. Thanks, everybody.
Goodbye.